Good morning, everybody. I am Becca Phillips, and I work at the West Virginia Water Research Institute in the Brownfields division. So I am going to be talking a little bit about some Rivertown projects that have happened in West Virginia and how Brownfield redevelopment was a role in that. And okay, great. Before getting into that, just a quick kind of refresher on what a brownfield actually is. And there's a formal definition by the EPA, but basically it's any property that might be contaminated based on previous use. So some common examples are things like former gas stations, abandoned railways, anything that has asbestos or lead-based paint, things like that. So these aren't so contaminated that it'd be like impossible to clean them up and reuse them, but they definitely do need, to be looked at and made sure that that's been addressed so they don't uh, pose a public health issue. So, some of the benefits to addressing them and getting them cleaned up after being assessed are listed here on the screen for you. And um, the ways that they can be redeveloped just kind of depend on the prior use and what they find when they assess the site, including like what contaminants are there and also how extensive the contamination is. But essentially, old industrial buildings can be turned into new real estate. New building can occur on those cleared sites, and then community infrastructure and aesthetics can be improved. And that can also include more green space and even some outdoor recreational uses. So, when we're thinking about river towns, something important to kind of be aware of, especially in this area, is the kind of earlier history when industrialization was starting to take place, and a lot of those sites did occur on the riverfront for a few different reasons. And it's largely economical and related to infrastructure, but it was an easy way to transport supplies, especially some of those heavier supplies before the railroads were installed. And then also being close to the water was helpful for manufacturing and even for like um, sourcing some of that power. So, like for steam engines and whatnot. And then, of course, historically, that was a great way to just conveniently dispose of your waste and just, toss it in the river, which we know now it's not a good practice. So, um, over the years, some of these sites, have become abandoned and vacant as the factories have closed, and not only being an eyesore, they were also like these underutilized spaces and potentially public health hazards because it's a safety hazard. There's contaminants that can affect public health. And so a lot of what's happening now is some communities are starting to get these sites redeveloped, and a lot of those reuse options more recently are trending towards like outdoor recreation and kind of getting into the tourism aspect of things. And like, this has been this gross industrial thing. What can we make it that really takes advantage of the beautiful river and, getting some of that area cleaned up so that we can actually enjoy it for us as a community and, not just looking at it as a way to make money. So, speaking of some recreational reuse ideas, there are all kinds of different ways that, depending on how the site was used in the past and where the contamination is, that it can be remediated and put to a different use. A lot of fun different options here that I'm not going to list out for you. And what I am going to do is go through two different examples of some things that have taken place in West Virginia that the Brownfields Assistance Center here in the Water Research Institute has actually been able to help out with and have a hand in. So when you do get these slides after the presentation, you can also click on this link here on this slide to see some more projects that we have done in West Virginia. This is not an extensive list, but it does show you like some of the history of the former sites and just like a quick summary of what we have been able to do to help with those communities. So let's get into the Morgantown Quality Glass Plant. So this site is located on the Van Voorhees section of Mon County, bordering the Caperton Rail Trail. The site was about 3 acres, and at the time that we started getting involved in the early like 2000s, it had 5 abandoned building structures that were full of some different hazardous things and some waste materials. There's like yucky bucket there is actually what the file picture is called. Anyways, so the plant produced opaque white light fixtures in the 1930s and through the 80s. And during part of that time period, it was serviced by the railroad nearby, which is now the rail trail. And they actually would supply the factory with bagged arsenic and lead. And the locals, understandably, were concerned that some of these hazardous materials from the site had actually leached into the groundwater over the years, which is exactly what happened. So in the 90s and 2000s, there were multiple environmental site assessments done to kind of help spark that remediation, because before you can clean it up, you got to know what exactly is there and kind of where it's located and how bad it is. And eventually, uh, remediation was conducted and completed in 2012 with the removal of the buildings. As part of the cleanup efforts, the site was entered into the state's voluntary remediation program, which is facilitated by the Department of Environmental Protection. And they entered into, this agreement to implement some deed restrictions on future land use and also some engineering controls so that the known contaminants would be appropriately addressed based on how the site was going to be reused. So it didn't have to be like every single contaminant needed to be removed and addressed. But since they knew, hey, we want this to be a certain thing, we can make sure that we take the appropriate measures so that public health is not harmed. The remedial action plan included construction of a soil cap over the contaminated area, and also that the site could not be used for residential purposes. And there were also restrictions placed on how the groundwater could be used because it was so contaminated by lead. And on top of the 2 feet of clay that they used to cap the area, it was also covered with 6 to 12 inches of topsoil, which was seeded and fertilized. So some of the things that the Brownfields Assistance Center specifically helped with during this process include applying for some grant funding through the EPA to get assessment and cleanup grants, and also securing some additional assessment finding to make sure that there was a very good idea of what was in the area and how extensive it was. We also assisted with engaging some of the stakeholders and providing project updates as well as technical expertise, because in addition to some of these environmental issues, there were also some zoning issues that needed to be worked through for this and the trail. And then we also helped with community engagement to explain the Brownfields process, what was found through the assessments, and, just talk to the public about what was going on and what could happen next. And in 2016, they did open up this kayak launch, and you can see some of these pictures from like the grand opening. And today it is now known as the Mon River Rail Trail head, and it also has some parking. So it's put back into some good use for the community, which is great. All right. So now we're going to move on to the Fairmont Box Factory. And this one started as a glass melt shop and recycling facility, which then continued to just be a cardboard box manufacturing facility. And a lot of assessments happened over the years because the community, could see this as an eyesore. It's also right by the river. So it's like, this is a great location. Can we please get this dilapidated building addressed so that we can use it for something else? And eventually in 2025, the structure was demolished, and there are now some plans that are happening in place because not everything is, ready to be ready for the new construction to happen. However, there are a lot of plans underway, not just where the Fairmont Box Factory sat over here in this Momentum Adventure Park area, but throughout this whole Beltline area. And excuse me, uh, the city has worked with the community over the years to get input and feedback on what these sites should become. And it's really interesting to look back through historically and see how some of that has changed. And like the most recent plans is to really turn this into some more recreational use for the community, which is great for public health and also helps with tourism too. There is a plan in place for the West Fork River Trail extension, where there used to be a rail line, and then also a skate park, pump track, bouldering facility, athletic equipment, viewing area, parking, and some indoor public amenities. And then over here, kind of to the right of where the Fairmont Box Factory was, but still along the river, there are plans in place to turn that into like some related recreational use, such as a soccer field and a multi-use sports court for tennis, pickleball, and more. So some of the services that we help provide for the area in general include some mini grants that helped with planning and visioning and securing additional funding. We also assisted with Fairmont applying for 3 different assessment grants, and then we helped with community engagement in general. And just to kind of wrap up, for our programs, we not only help with projects throughout the state, we are also now the regional provider for free technical assistance. So anywhere in the Mid-Atlantic, I know we've got some folks from Pennsylvania here as well. So we can help you too through our TAB program, which stands for Technical Assistance to Brownfields. And this is just an example of some of the services that we can provide through either program and some of the ways that we help support brownfield redevelopment. And that's everything for me today. Thank you so much.
Good morning. My name is Zainab Jawad. I'm a PhD student in civil engineering. And for my PhD, I've been working on the heap leach project under the title that you can see, the extraction of rare earth elements from Appalachian coarse core refuse through heap leaching. In this presentation, I will guide you through the progress we've made with this project and our key findings. So let me start with a background. Prior to delivery to power plant, as we know, a mined coal must undergo a process known as preparation. In coal preparation plants, the material is separated into two streams. The first is the product, the coal itself, and the other one is the reject or the waste. This known as the coal refuse. One type of that refuse is the coarse coal refuse or CCR. And the previous research has found that the majority of rare earth elements, as we know, those elements are very important for modern technology. They're presented in the reject stream of coal preparation plants, especially the CCR. Those materials are usually dumped or stacked as piles in open areas within the mine. And once exposed to weathering conditions such as oxygen and water through rain, it generates its pyritic shale oxidizes and it generates acid drainage. So the hypothesis that this project was built based on that this the process of pyrite oxidation could be quickened and the RE extraction from the coarse core refuse could be accelerated through the recirculation of the acid drainage. Our main goal was to evaluate heap leaching at bench scale or lab scale as a mechanism to extract the rare earth elements from the coarse core refuse. I mentioned heap leaching a couple of times, so I want to explain the meaning of heap leaching. So when we say heap leach pad construction, we mean the process of building a heap or a pile of the ore of interest, and in our case was the coarse core refuse. And it's usually built on impermeable liner for environmental containment, and then a leaching solution is usually applied to the top of the heap where the element of interest is usually selectively removed. So we wanted to mimic this process in the lab. So one of our objectives was to determine which type of core refuse would give us the best results. So we collected the three types of core refuse. The first two types were from the Monongalia County mine, known as the Blacksville number 2 coal mine. The first one, I will be referring to that as weathered coarse core refuse, and that was about 5 years old at the time of collection. So that means it has been exposed to weathering condition for 5 years. The other type from the opposite side of the impoundment of the area, I'll be referring to that as a fresh, and that was about 2 years old at the time of collection. We also collected a acid drainage or acid mine drainage from the Coarse pond available at the site as well, and this pond was chosen based on its low pH and high RE concentrations. We also collected a third type of coarse core refuse that was from the Loveridge mine in Marion County, West Virginia, and that was collected right from their prep plants, and that has never exposed to any weathering condition, and that's why we gave it the name raw. So as I said before, we are trying to mimic the process of heap leaching, but in the lab. So the first test that we chose to do that was the column leaching test. So we did 2 rounds of column leaching testing. The first round, we used the weathered and the fresh refuse. We filled 6 columns, 3 for each type. And then we used 3 leaching solutions. The first one was the acid drainage, the acid mine drainage. And the second one, acid mine drainage with added hydrogen peroxide as an additional oxidizer. And the third one was the DI water. We did the testing for 6 weeks. During the first 3 weeks, we did one leaching cycle per week, and then we collected a sample by the end of the cycle, and then we sent it to the lab for testing. We stopped for 1 week for data processing, and then we decided to go with multiple leaching cycles after that. So we did 2 leaching cycles during week 5 and 6, and then by the end of those cycles, we collected a sample and sent it for testing. During the second round, we used the raw refuse, and we modified this round based on the results of the first round, and we used the acid mine drainage and DI water as leaching solutions. The idea was here to leach as frequently as possible. And then so that once the discharge from one cycle stopped, we start the following cycle. But then we decided to terminate this test by receiving the results of the 10th leaching cycle, and we will know why in the results in a little bit. So this is the setup of the column leaching test that we did in the lab. So for our key findings, we found the first important finding was that a combination of weathered coarse core refuse with AMD as the leaching solution gave the best results. Weathered refuse had the highest leaching potential when we compare it to the other two types. And there were 3 reasons behind this finding. The first reason is that pyrite oxidation has already taken place within the weathered refuse, and RE compounds were made readily available at the surface of the refuse. And that was evident through the results of the paste pH. We know that a value of less than 6.5 means that the material under testing has already gone through the weathering process and has already generated acidic sulfate salts. And we can see those numbers like were further weathered than the fresh were less than 6.5. Well, when we compare that to the raw, we can see that has a high number, and then the results were insignificant for the raw refuse, almost 0 for total REs, and that is indicated by the orange circles in the figure. The second reason was the high moisture content within the weathered refuse, and we know that water is very important for oxidation. The third reason is the small particle size range of the weathered refuse, and that's again due to weathering. So as the particle size decreases, the surface area available for oxidation increases or becomes bigger. So I'll continue my results with the column that gave us the best results, which is the one that filled with weathered and AMD as the leaching solution. Also, another very important key finding is that most of the leaching occurred within the first leaching cycle. And then the multiple leaching cycles that we did during weeks 5 and 6 did not promote RE extractions. And that, again, as I said before, prior weathering and oxidation has made the REs compound available at the surface. So the first cycle was enough to flush most of the REs out. So we didn't see any significant increase after that. Other results is that the highest percentage of total RE leached from solid were less than 2%. And total major metals, examples that iron, aluminum, followed the same trends that we've seen with the total REs. Then we decided to scale the size of the testing. So we went from columns to drums, size 55-gallon drums. And that was done to eliminate any possibilities of preferential pathways that the leaching solution might follow due to the small size of the column. So we used the weathered refuse with AMD as the leaching solution based on the results of the column testing. And then we did 2 phases of testing of leaching. The first phase, the purpose of that was just to mimic the plan that we followed with the column testing during the first 3 weeks to compare the results. And then we had an extended drying period of 4 months. And then once we started phase 2, we started by 1 leaching cycle for each drum. And then we modified the schedule for both of them. With the first one, we followed a shorter drying period of 2 weeks for the first drum. And then for the second one, we applied humidified air as an engineering control. And then we applied it for 6 hours. That was enough to fill the voids within the coarse core refuse. And then we sealed the whole drum. By the end of the 2 weeks, we did 1 leaching cycle for each drum. This is the setup of the the drum leaching test, and this is how we applied the humidified air, and then we sealed the drum, second drum. So when it comes to the result, this is the result of the first phase. As I said, that was just to compare to the results from the column testing. And as we can see here, that the results of the drum testing confirmed our results from the column testing, with the first leaching cycle producing or extracting most of the REs out, and then with limited or not significant increase after that. Here I'm showing the results of the first phase and the second. I talked about the first phase, and now we can see that the influence of an extended drying period of 4 months was observed through the first leaching cycle of phase 2. That cycle doubled the amount of total REs within the leachate. The percentage increase of the total REs was about like a little bit more than 100% for both drums. Well, when we compare the first cycle with the second, we've seen again a limited increase with the second, which was like after 2 weeks of a drying for the first one, and for applying humidified air for the second one. That was similar to trends seen with later cycles in phase 1. The results of phase 2 showed that the percentage leached from solid was increased to the value of between 2 to 2.5%. So here I'm just showing the individual REs that were leached out, and we can see the consistency when we compare the results of the first column to the 2 drums. So here I'm going to end with a general conclusion. So in our conclusion, we found out that the age of the refuse plays a very significant role in the process. The oldest gave us the best results, combined with AMD as the leaching solution, and we found out that an extended drying period of 4 months, for now at least, can add like a can allow for an additional pyrite oxidation, and allows for the RE compounds to accumulate at the surface of the solid refuse, So that's why we decided to go with our next step is to evaluate a shorter drying period, which considered like a midterm of 2 months, just to determine our optimum drying period that would give us the best results. And before I end this, I just wanted to acknowledge the financial support that we received for this project from the Department of Interior Office of Surface Mining, Reclamation, and Enforcement, and the in-kind support I received from the WRI Fox and the American Consolidation Natural Resources ACNR during field visits and during lab testing. Thank you very much. And I'm happy to answer any questions if you can leave the questions in the chat.
So good morning. My name is Mills Langehans. I'm with the West Virginia Water Research Institute, and I'd like to talk to you all today a little bit about mine drainage reclamation in Lambert Run. So just getting started here. I can switch to the next slide. So I'm going to go through where this is at. I'm going to go through a brief abandoned mine drainage overview, and then specific impairments in this watershed. And then I would like to talk a little bit more specifically about a couple of our treatment systems, including Lambert Site 4, which was recently completed, and then Lambert Site 7, which we are upgrading / remodeling. So here's the background. So where this is the Lambert Run drainage. This is a map of the Lambert Run drainage. It's 8 square miles, and it is part of the Limestone Run watershed. This is just outside of Clarksburg. It's a little bit northwest of Clarksburg. And actually on this map, you can see towards the top right, there's Spelter. So just to give you an idea of where this is, you can see it's been extensively mined, and most of those streams are impaired, and it was recognized for impairment in 1996 and added to the 303D list of impaired streams, primarily for pH and metals. So again, super brief overview of abandoned mine drainage. There are a couple different types. generally how this happens is mining occurs and that exposes sulfide minerals. Something with this would be something like pyrite. And so those sulfide minerals oxidize and react with water and release sulfuric acid. That will bring the pH down and produce really acidic water. When that acidic water interacts with the rocks and the geology of the area, it dissolves the rocks and lots of metals leach out and are now free flowing in that water. So we get these impaired streams. So that is generally acid mine drainage, one of the types of abandoned mine drainage. There's also alkaline mine drainage, which is actually what is going on in Lambert Run in this drainage area. So one way that alkaline mine drainage happens is we go through mining, the sulfide minerals are released, the pH drops, and those metals are leached out of the rocks. And then it can also, if that water flows over carbonate-rich rocks like dolomite or limestone, it will actually bring that pH back up a little bit, but those metals are already in the water. They'll change from dissolved metals to particulates depending on the pH, but in fast flowing streams, those particulates are still taken away to wherever the streams are going to. So it's a little bit of a problem. This is just a picture of abandoned mine drainage stream. As you can see, it's got that highlighter orange color. I know in West Virginia, this may seem like a relatively normal stream for us, but it is not. Streams are not supposed to look this way, and this is really indicative of high iron with that orange color. So moving on back to Lambert Run. In 2003, Guardians of the West Fork developed a watershed base plan for this. And since then, WRI and Guardians of the West Fork, in conjunction with agencies like the West Virginia DEP, have worked on various passive treatment systems in this area through Section 319 grant funding. So far, there are 7 passive treatment systems in this area. That's what those little stars are. And then there are 3 remaining identified project areas that we have not gotten to yet, but will. Today, I want to talk about 2 sites. This first one is Lambert 4 in that yellow circle. And then the second one is Lambert Site 7 in that green circle. So moving on to Lambert 4. This site recently was constructed in September 25, but before that, it had a pH of 7.64, which again is a relatively high pH. Usually when I see water chemistry like that, I think, oh, it's not that bad. It still can be. So, for instance, here, this stream with pH of 7.64 was still contributing, or the source was still contributing 0.5 tons per year of iron into Lambert Run, which is why we went in and constructed this wetland, which holds 71,500 gallons. I have a couple pictures showing what that looks like up here. Yeah, so the picture on the left here shows what it was before, just a big open field, and the stream and the source run behind here and then curves around where that tree line is. That's on the left, and then on the right, post-construction, we have that wetland there, and the grass is a little low, but that's because it was new. It will grow more, hopefully. What it looks like now, all of the grass has died down, but what's really great is it's still showing a reduction in some of these impairment parameters. So far we only have 10 total samples, which is about 4 months of data for us, which isn't a lot. But going off of that, this is showing a 70% reduction in total iron. Influent would be about 2.88 milligrams per liter, and effluent is below 1, which is great, especially since half of this data has been in winter months where there is less wetland grass in that treatment system. So moving on to Lambert Site 7. This is a very large system. Pre-treatment data, we have pH of 6.6, again, relatively high from what I'm used to seeing, but we do see that it was still contributing 0.25 tons per year of aluminum and 45 tons per year of iron. This is by far the largest source in the watershed. Commonly, this exceeds 1,000 gallons per minute discharge. So back in September of 2015, treatment system was constructed that consisted of 5 aerobic wetland cells. And upcoming, I'll have an aerial picture to show you of what that looks like. But after that was constructed, we see pH comes up a little bit more, a little bit closer to neutral. And this showed actually a 70% iron reduction and a slight aluminum reduction. But we found that it was still discharging over 5 tons per year of iron to Lambert Run. The goal is 0. So here is that aerial image of those 5 wetlands. The treatment system, the flow in this moves from left to right. So if you look at that leftmost pond, you can see it's got that really bright orange abandoned mine drainage color. But then if you look all the way to the right, it's relatively clear, which is just really cool to look at and see firsthand. But like I said, this is a very large treatment system, so one picture would never be able to cover all of it. It's of roughly 4 acres. So this aerial image, I think, is kind of the best way to view this. But moving forward, so I called it Site 7 upgrades here. It's really more of a remodel, just because of how much we are doing to it. The goal is to be at a 95% iron reduction, so we want to move up from that 70% to 95. In order to do this, we have decided to change a couple things. So that first wetland will be changed to 2 ponds, so that the water has more time to slow down and spread out, and so some of those particulate metals can settle out and get out of the free-flowing water. In addition to this, other wetlands will be expanded, so we just have, again, more retention time, more time for those particulates to get out of the water. Interestingly enough, we're able to use some of the extra soil to recover a nearby high wall. This was something that we ended up pivoting towards and kind of jumped at when we realized we could do it. So that's really cool. And on the next slide, you'll see a map of some of these engineering plans to give you a visual reference of that. We're hoping to have this done by fall of 2026. And like I said, this is a very large project, and the cost of the project does reflect that. So projected cost is $1.1 million, and this is again funded through the 319 program and Abandoned Minelands program, thankfully. So some things to check out with this. I have, whenever these slides get released, that first link there is a link that the DEP did a drone flyover of Lambert Site 7. So if you want to go check that out, get more of an idea of what it looks like instead of just my aerial pictures, that is a really cool video. And then also WRI did put out a story map just on Lambert Run in general. So some of those other treatment systems, the 5 other treatment systems that I didn't cover here, you can go look at and read a little bit about and get a little bit more history whenever these slides get released. So here is that image of what the plans are. As you can see, that first wetland on the left, we're going to change it into 2 ponds and then expand wetlands 1, 2, and 3. And then if you see earthwork fill areas, that's actually where we're going to take some of that excess soil and reclaim the high wall and kind of just make those slopes a little bit more gradual and more natural to the area. Acknowledgements. West Virginia DEP and Guardians of the West Fork have been a huge part of this, as well as WRI. And then, of course, landowner support is huge for this. Most of this would not be possible without that. So, questions whenever we're wrapping this up? Thank you.